Okay, let's get started with Chapter 5. In Chapter 5, we will talk about energy from combustion. Occasionally when I talk about combustion, you will hear me use the term burn. So if I use burn, that means combustion. If I use combustion, that means burn. In this particular chapter, we'll be talking about what are fuels, and what you will discover is that for the most part in this chapter, we will talk about fossil fuels or, again, hydrocarbon fuels. How is electricity generated? That's going to be a pretty important topic. You're going to see how mechanical energy is used to help, to generate, in fact, do the work to generate electricity. What are the positive and negative consequences of burning carbon-based fuels? And there are consequences to the environment. Many of them create greenhouse gases and other pollutants in the atmosphere. How much heat is released when fuels are burned? And you're going to discover that the amount of heat is proportional to the hydrogen and carbon content in that hydrocarbon ratio. And what are biofuels and what are the benefits of using them as transportation fuels? We'll learn about that, what happens in such examples of using ethanol in the fuels. So here we are on this, the first slide here, combustion. The verbiage on the right, we'll take a look at that, then we'll look at the diagram on the left. So on the right, you see there are three requirements to generate a fire, okay, to start combustion. Okay, a source of heat, a source of fuel, and an oxidizer. You must have all three of these present in order to start a fire or in order for combustion to occur. And we show you this in the equation. You have fuel plus oxidizer plus heat gives you the product. And we note that the majority of fuels are hydrocarbons, compounds made up only of hydrogen and carbon atoms. And on the left, we have our fuel, basically our triangle, our combustion triangle, which is composed of fuel, oxidizers, and heat. And if you take away any one of these legs, you can actually start a fire. All right? So there we have it. We take what? These three requirements, right? Fuel, oxidizer, heat. We get our products, right? And that's important to combustion, and that's what combustion is about. It's about taking these, and the majority of the fuels we have are hydrocarbons. That's carbon and hydrogen is what we have. And occasionally when we come to biofuels, you're going to discover that we have carbon, hydrogen, and some oxygen. You're going to discover that the BTU of that is slightly less than that of carbon and hydrogen. So this is combustion. So the bottom line of combustion is, for us, in terms of thinking of energy, is we take a carbon-based material, we heat it in the presence of oxygen, and we get products. For efficiency, it's going to be what? CO2 and water. So now let's take a look at the triangle on the left side here. So we have fuel, oxidizer, and heat. So here's how we stop combustion. If you take away any of these legs, it stops. Follow? That is the bottom line. That's what they call the triangle. So here, if there's no fuel source, you can have heat, you can have an oxidizer, you won't get it to go. If you have fuel, heat, and no oxygen, then it won't go. This is, in fact, and if you take away heat source, then it won't go. So let's talk about this relative to forest fires. Okay? This is why forest fires work and burn so well. And that sounds kind of, let's say, burn so well. Well, they do. Because oxygen is, right, the air is there. Fuel, you have lots of trees, right? Lots of brush, lots of carbon source. And heat, occasionally you have natural things like lightning that happen. Then you have natural materials that tend to combust. And then you have then you have good, kind citizens who throw cigarette butts out the window. Okay, I'm sorry, they're not idiots. I apologize for that use of terms. We shouldn't have said that. As a heat source. So you get a heat source, and when it starts, lots of oxygen, lots of fuel, doesn't take much heat, and that's what happened. Yes, sir?
One of the largest forest fires in California last year was actually started by somebody getting a flat tire and their rim hitting the road.
That's exactly right. That's exactly right. Any source of spark. That's what I say about it. But the ones I worry most about are those people that throw things. That you're out in that area and you throw a cigarette butt out, or you forget to put out a good campfire. But that's exactly right. It doesn't take much of a spark to get it going, and that's why these forest fires. People, wow, how did they do that? It's just nature. Example, friction creates that spark. That's the source of heat. That's exactly right, and that's pretty incredible, isn't it? And so what do they do? They dig or make a fire break here. Okay, so that's why they go out and they plow down all the trees, or they'll burn in front of the fire. And you say, they started one, yeah, but that's a controlled burn so that they'll get rid of the next level of fuel source. And that's why they're doing that. All right, when you see them digging breaks and things of that nature. Here, the oxidizer, this is when they're dumping things on it. The powders that they dump on it to smother it from the oxygen, to keep it away from here. Once the heat gets going, it's just going. You get it? And it sparks. Once you get the spark, the rim hitting the road, yeah, it happens. And that is why we see the forest fires that we see. And some of it's just natural. Nature just does it occasionally. Okay? All right? So be aware of that. So this is combustion. This is what you're doing when you burn your campfires. All right? Hydrocarbon combustion. This is what we were just talking about. The combustion reaction features a fuel and oxygen reactant. That's on the left side of the arrow. So the fuel is a hydrocarbon. This is C4. This is butane. This is your cigarette lighter. So this is butane plus oxygen. So the left side, and the carbon dioxide and water product on the right side. Is this complete or incomplete combustion? What's the answer? How do you know it's complete combustion? One thing you have to look at is CO2. You get CO2, it's complete combustion. Be aware of that. Okay, I will ask that type of question on the exam. All right? Complete combustion, CO2. Incomplete combustion is carbon monoxide. And by the way, your equation has to be balanced. Okay? I will probably post some tips on how to do balanced equations for you. So we'll post something on that, I think. Help you out. Okay, so it's a balanced equation. So this is a reaction, again, of butane. This is what's in the cigarette lighter. It's butane because it's really easy to handle in a cigarette lighter. It doesn't go boom in your hand, okay? And it doesn't burn out of control. So it has the right BTU just right for being used in cigarette lighters. And so again, we have the proper balanced equation, and it has to be balanced. And you'll balance the equation by simply counting the atoms. For example, we have 8 carbons here because that's 2 times 4. Here we have 20 hydrogen because that's 2 times 10. Here we have 13 times 2, and that's going to be whatever that is, 26. Yeah, thank you. I almost needed a calculator, right? Okay. Thanks, sir. Then we have 8 times 1, 8 times 2, etc., and we get the right number. The actual combustion of fuel is never this simple, however, and be aware of that. It is never really that simple. Fuel contains a variety of different hydrocarbons and some other sulfur compounds. When they contain sulfur compounds, they blow out into the environment what's called the SOx, the SOx. SOx are what? Pollutants, which you now know, right? So this is where the SOx come in. The other one they burn out is NOx, and that's due to other things. And occasionally people there'll be additives and so it's never really that simple. In addition to high temperature, nitrogen, there it is, from the atmosphere also reacts with oxygen to produce a variety of NOx pollutants. You follow? So it sucks the nitrogen out of the air, okay? And you get the NOx and the SOx. The catalytic converters are doing a pretty good job of dealing with the NOx, less so with the SOx, but certainly catalytic converters are used to ensure complete or more efficient combustion. All U.S. vehicles, and I think vehicles around the world now, are required to have catalytic converters, and the reason is so you can get efficient combustion. Got it? Now, the environment wants efficient combustion because you want to keep the environment clean. You want efficient combustion because you want to drive like me down the road in your truck. That's right. I want my truck. I want to hear the roar of my engine. Okay? Follow? So that's why I want complete combustion, so I do my best to keep my vehicle tuned. And since I use fossil fuels, I plant trees, compost, recycle. Get it? Hopefully you're getting that message right now. What is energy? It's something that you don't have in my class sometimes. That's called lack of energy. Okay? All right, energy is a capacity to do work. That is the basic definition that will be asked over and over again. It is the capacity to do work. Circle that, know it over and over again. It is the capacity to do work. All right? Now, that capacity to do work, we're going to talk a lot about machines in this particular chapter, in chapter 5. So when we talk about capacity to do work here, we're going to talk about the capacity of machines to do work. Your vehicles, power plants, et cetera, et cetera, et cetera. Okay? And when we look at that energy, there are two types of energy, and you want to catch these concepts because I do like to ask these, and these are pretty important concepts. Potential energy is energy due to position or composition. In other words, because of where that material is placed, or that item is placed, or the composition of that, it has potential energy. For example, does anyone here eat donuts? Oh, but Krispy Kreme, yeah. Listen, I am a Krispy Kreme. I'm sorry, he just pushed the button. My favorite fuel source of carbon burn is Krispy Kreme, but I cannot buy Krispy Kremes unless it's from the original Krispy Kreme location, which is at the Oakland Mall, closest one to Oakland Mall in Detroit. It used to be at Corona Road in Flint, but me and my son put them out of business. Okay, we always make the hot light. But anyway, that's a different story. So you get it, donuts. Maybe. Okay, now I have to bring the entire class donuts one day. All right, we got it. All right, but here it is. The donut, right? Anybody do that 5-hour energy? You don't have to raise your hand on these kinds of things, by the way. 5-hour energy, they do the drinks kind of thing. All right, anybody do the coffee thing? Yeah. Okay, the coffee, you got donuts, right? You got 5-hour energy. Okay, for some of you get up in the morning, you go to Taco Bell, whatever it is, you go to McDonald's. Okay, that's energy. These are energy sources. But if they are just sitting there on the shelf, right, they have potential energy. Get it? The coffee has potential energy. Krispy Kremes. The Krispy Kremes have potential energy. You get it? So everyone follow. But that energy sitting there doesn't do anything. Okay. Follow? Is everyone with us? That's called potential energy. It's standing still. You have potential energy. If you're standing still, that's it. It's potential energy, not going. But when that energy starts to move, it's called kinetic energy. For example, if I throw the Krispy Kreme donut, okay, I have now turned that into kinetic energy. All right? You get it? Because it's moving. This is kinetic energy when you wave your hand. All right? Not waving your hand is potential energy. Does everyone follow? So the Krispy Kreme, they have energy inside them. When you eat them, then it's converted. You got it? It's potential energy. So energy standing still, or the composition, is potential energy. So here's your test. If I throw a baseball, kinetic or potential? Which one? Kinetic. If I hold a baseball, kinetic or potential? You get it? If I catch a baseball, potential or kinetic? Because it's standing still again once I catch it. If I toss the baseball, kinetic. You want to be aware of that because those type questions I in fact ask you. Does everyone follow? And I love to ask the baseball one. All right, if I catch the baseball. And that's occasionally I give away the points because students argue and they say, well, I kind of felt it was moving. Okay, I got it. As long as you understand the concept. This is important. Potential energy, kinetic energy, because this is how we generate the lights and the things we have. We have potential energy in the coal sources, in the fuel sources. We put them into the furnace. We burn it. That potential energy is released in the form of heat. That heat, you're going to hear it over and over again on Wednesday, is going to convert to steam. Steam is going to turn a wheel. That wheel is going to turn a turbine. The turbine is going to give you electricity. Potential energy, kinetic energy. Energy standing still. Kinetic energy is energy movement. A general rule of thumb when it comes to potential energy, it has more potential if it's higher off the ground. when it comes to turning it into mechanical energy. We'll talk about it a little bit later. It'll make more sense to you. Okay? The further the fall, the more we generate energy from it. Follow? Okay? All right. So work is movement against force. You always work, you're moving, okay, against force, and it equals, work, yeah, is moving against force, right? It's force times the distance. How far do you go with that force? So that's how you know you did work, okay? For example, some of you this morning did work when you got up out of your beds and you made your beds up, right? Right. Which I think is one of the most ridiculous things in the world ever created, was making a bed. What value does it have? Please tell me. Someone's going to figure that out.
It's just an aesthetic value.
Oh, aesthetic value. Okay, now I understand it. But it's work. You get it? It is work. Do you follow? You did work. You move force against distance. Each time you walk, when you walked to class this morning, you worked. Okay? And so it was distance times the force. And some did it better than others. What you're hearing in this first lecture are a lot of concepts that you want to get. These are a lot of definitions. And so we're trying to introduce you to these definitions so that when we do the second part of Chapter 5, okay, you're going to use these definitions. So everyone follow how this works. Heat is energy that flows from a hotter to a colder object. That is critical. You will be tested on this. Heat is energy that flows from a hotter to a colder object. So if an object is cold and another object is warm, the heat is going from the warm body to the cold body. For example, when you walk outside, today is only about 40, so that's pretty good in Michigan, 36, somewhere there about. Man, we're like, it's time to sunbathe, right? So it's like 36, 39, 40 degrees outside. Where your and that's, I'm talking in F now. That's unfortunate. Your body is what, 90, what is it, 98? 98.6, thank you, because I remember more about 40 in C. 98.6. So you have your body temp. And so your body temp is 98.6. Outside is 40 degrees. I'm talking F. I apologize. We're talking F. If you're about 40 F, which way is the heat going to go? What's going to happen to your body? Your body gets cold, right? It's not because there's cold air blowing against you, which it is. It's because your body is giving up the heat. Does everyone follow? Your body is releasing the heat, trying to warm the outside. That's why the colder it is outside, you get really cold right away. As soon as you walk out, you're like, it's frigid. Your body is attempting to release its heat to the outside environment. It's trying to warm outside. It's trying to warm the entire outside. You get it? It wants to come to equilibrium with the outside. And if it's very cold outside and comes to equilibrium, it shuts your body down. Follow? Yeah.
So is that why, like, have you ever seen a show like Naked and Afraid, where they're like out in the wilderness and they're naked and they like to cuddle up together?
That's why they like to cuddle up together. Yeah, that's one of the reasons. Yeah, because they're trying to conserve body heat. And the reason they cuddle together is that way whatever is pointing outside, that's the parts that are being sucked out, and the rest of it's staying warm. Okay? Because the environment is sucking the heat away from you. It's not cooling you. It is cooling you. They follow? The result is you get cool. Does everyone follow? But the direction of the energy flow, and that's what we're talking about. We're talking about direction of energy flow, not the result as much. So the direction of energy flow is always hot to cold, and that's important. Okay? That's why when you drink your coffee, what happens to your body? Warms up, right? You get it? Okay? Because your cold body is being transferred in the direction of the warm fluid. And this is a very important chemical or physical science phenomena that you want to be aware of. It's always cold, hot. That's why Grandma says, close the door, you're letting all the heat out. She's right. Okay? You get it? You are letting all the heat out. Okay? And that heat's trying to do what? Trying to warm the entire outdoors. Differentiate heat from temperature. Very important. You have to differentiate heat from temperature. That is a critical feature, phenomena that you have to differentiate. Okay? So make sure we differentiate heat from temperature. So we know what heat is now, right? From hot to cold. Temperature is a measure of the average kinetic energy of the atoms on the molecules in a substance. All of them have an average kinetic energy. You have an average kinetic energy of 98.6 Fahrenheit. Follow? A dog has an average kinetic energy, and I don't know what that is, actually. I should know that. I don't remember it now. I remember it when I'm walking across campus. So everything has an average kinetic, and that's when you put the thermometer in it and you read it. Okay? That is temperature. That is not heat. Okay? Does everyone follow? If you put a thermometer in it and you measured it, that's called temperature. But we do say, how hot is it? Okay? Does everyone follow? All right? Don't confuse the verbiage with the physical science. Okay? Does everyone follow? Note, heat is a consequence of the motion of a molecule at the molecular level, whereas temperature measures the average speed of the motion. You get it? So there's this heat that's generated because this is what molecules do. They vibrate, they shake, and temperature measures the average of that motion. And that's what happens. So be sure that you pay attention to the slide and differentiate it. You will get questions on it. The units of heat. The units of heat, very important also. Well, I keep saying on each of these slides, but now you know that my slides are your study guide, right? And so that's why I keep saying I have the critical points that I really want to make sure you definitely don't miss are these. Others I'll tell you in addition to. So here we are. Important. The joules, 1 joule is the amount of energy required to raise 1 kg of object 10 centimeters against the force of gravity. CHEM102A, you don't have to memorize that one definition. Whew. You simply need to know that energy is measured in joules. Scientific energy is measured in joules. For CHEM102A. 102B, we'll have to memorize that entire definition and use it. Okay, so if you have friends taking 102B, tell them, yeah, you have to memorize it. Okay? So we have joules. Another important unit that's used to measure it is calories. 1 calorie is the amount of heat required to raise the temperature of 1 gram of water 1 degree C. For 102A, I'm not requiring you to memorize that definition. Simply know that calories are another unit to measure what? Heat. For Chem 102B, you will have to memorize the entire definition there and use that definition. 1 calorie equals 4.184 joules. I think I'd like for you to know that simply because I like to ask it. Here's what you need to know. Okay, so you got it? So scientific units of energy are what? Joules and calories. Got it? Okay. Now, it's important that you differentiate that from dietary calories. Okay? When we talk about calories as scientists, we're not talking dietary calories. And note here on this particular slide, we have 1,000 calories, scientific calories, is 1 dietary calorie. So everyone follow that. So an average anatomical male needs about 2,200 dietary calories. An average anatomical female needs about 1,500 of those. So in terms of scientific calories, you multiply that times 1,000 to say how much how much heat or how much energy you need in a scientific fashion. Does everyone follow? Important that you know this. I do expect you to know this difference, that 1,000 scientific calories, and I use the word scientific calories to differentiate from dietary calories on purpose in 102A and 102B. So you have 1,000 calories, which scientists like to measure. They measure this in the laboratory somewhere, and equals 1 dietary calorie. So the key take-home point here is that dietary calories are not the same as scientific calories in terms of its units. Got it? But they can be converted. Now let's take a look let's take a look at the joules for this. Someone Google real quick, joules for a heartbeat. I think it's 1 or 3. So let's take a look at this diagram here. Comparisons of energy, and I think a heartbeat's about 1. It's either 1 or 2 or 3. I should know that. It's about 1, I believe it is. Yeah, I'm pretty sure, but we'll find in a minute.
1 joule per beat.
1? Okay, good. Okay, yes, what I thought. So heartbeat is 1 joule. Good, thank you. So here we just show you examples of what that energy looks like. So each time your heart beats 1, all right, that's a joule. Each time you pick up your calculator, that's a joule. So some of you use a lot of joules, right? Particularly during class. I mean, each punch you're doing, that's a joule. You get it? All right? In the class, you use up all your joules, man. Okay? And your data as well. All right? So here you have it. 1 joule. And so that's about here. So a heartbeat and picking them out. So just basic simple motions about a joule. And here are your AA batteries. Okay? What's that? 10 to the 3. Yep. 10 to the 3. Here. And so it's 1,000. And light bulbs, 10 to the 6. So a fair amount. And this is a lot. And so just to show you, atomic bomb is here, 10 to the 12. So this was Hiroshima. Okay? It's a lot. And a barrel of oil. So when the BP oil event happened, a lot more barrel, right? For a lot of energy here. Here, we start to get very small. Molecules operate down here. Content of a single sugar molecule is here. That's of a single sugar. Now, here's something you want to understand about sugar. Sugar is what we burn. We burn sugar, glucose, et cetera, et cetera. But sugar does not give you instantaneous energy. Okay? Be aware of that. Okay? Sugar does not give you the instantaneous energy. So when grandma says don't give those babies candy because they'll be too hyper, she's wrong. Okay? I once said that, and there was a grandma in my class, and she explained to me that I might know science, but she knows kids better than I ever will. I said, thank you very much. Okay. All right. They might get excited because you gave them candy. Okay. But look at the energy here. You get it? It's not an instantaneous burst of energy. It has to be processed through your body and exhale the CO2 and eliminate less water. Okay? So here you have it. I do like for you to know the movement. If I ask you, you move your calculator once, I like for you to know that's a joule. Your heart beats once. That's a joule. I do like for you to memorize and know that. Yes, sir.
So this is a really random question. I have a heart condition, so would my heartbeat require more joules?
Not necessarily. No, it still uses 1, but it may, I don't know. I'm not a medical doctor, by the way. Let me make the statement first of all. I have no medical advice here, but it may require a little more energy. Okay. Yes, depending on it. Okay?
I was just curious.
Yeah, but the reason it might not be exactly due to the heart, might be due to the rest of the energy to get there. So it might. I don't know. That's a good question. Interesting question. At least you're thinking about it. Yeah, good question. All right, so there we have it. That's our energy. So let's talk about how this energy works. This energy likes to fall off a cliff. Okay? And so we show you here how this energy falls off a cliff when we burn it. And depending on what we burn is what? Combust. Complete combustion gives us what? CO2 and what? Water. Incomplete combustion gives us carbon monoxide, okay, which is a silent killer, poison gas, can't smell it, don't see it coming, it just kills you. Here's what happens when we burn several fuel sources, okay? And this is why these fuel sources are used in certain applications. It's because of the amount of energy that they release upon combustion. And they release energy because they have potential energy. They're the donut, they're the Krispy Kreme. They're your coffee, they're your chocolate. So here we have methane. Methane, which naturally comes out of the ground, right? It is a greenhouse gas, but it has a fair amount of energy if you combust it. If I use the word burn, I am saying combust, okay? I have a habit of saying burn that probably will not change, okay? Combust. So if the energy combusts here, we get 50 kilojoules per gram. If it is negative, that means it releases the energy. Okay? So negative sign simply tells you that it released energy. Negative means it fell off a cliff. So the cliff here was 50 kcals per gram in terms of its energy level. Does everyone follow? That's how much energy was there potentially. So it fell off. Next we have C8, octane, that's in your fuel tank. That's one of the part of the fuel tank. When it falls off a cliff, it generates less than methane. So if you really want a real big bang in your engine, you put methane in it, but that's not a smart thing. Your engine is designed to contain methane and burn methane. It will blow your engine apart. Follow? So everyone follows. But to show you, you get more energy here, okay, from methane than you would from octane. Does everyone see that? See what I mean? This is a higher cliff, next cliff down is coal. And you're going to learn more about coal sources, I think, in the latter part of this chapter. Coal, most coal source, about 33 kilojoules. That's the height of its cliff. These are exothermic reactions. They give off energy. Exothermic reactions release energy. Then the next one is 26. Here is ethanol. So you see, ethanol in terms of its release is somewhere in the ballpark here, but that's a lot of difference. That 6 matters in terms of how your engines run and how the machines operate. So here, and note here the oxygen required, little different levels of oxygen, okay? And this 25 over 1/2, an engineer wrote this. A chemist would never write it that way, okay? All right, so an engineer wrote it. Ethanol here requires a little more oxygen, and here wood, this is what you naturally burn. You get pretty good burn when you burn wood, right? You get 14. So these are the cliffs. This is the potential energy here, and that energy is released, and we generate, again, complete combustion. And this is kind of the midway point here, okay? When you burn coal, right? You're basically doing, you generate only CO2. All right. Let's see, what else should I tell you? Note again, basically, as the ratio of hydrogen and carbon decreases, the heat combustion decreases. That is an important statement to hang on to in terms of what you'll be studying. Okay, and we'll try to go over again this on. We'll try to go more of this on Wednesday. Also note, as the amount of oxygen in the fuel increases, the heat of combustion increases. Okay, so we have that happening. These are 2 trends that I'd like for you to hold on to. Okay. We've already mentioned to introduce the concept that this is fall off a cliff. Well, in fact, this author shows it fall off a waterfall. Exothermic reactions, they release heat. That's potential energy at a certain energy level, and when it falls off that energy level to a more stable condition, which is CO2 and water, it releases the energy that's contained within its bonds. Here, show energy reaction of methane. Here, difference of energy level of going down. This is 802 kilojoules of going down here. Okay, when energy is released during the course of the reaction, it is said to be exothermic reaction. This is the energy that's used to power machines. Exothermic reactions, note this, are used to power machines. If it's a mechanical device, and it needs energy, power plants, engines. So if it's an engine, okay, it's going to run by an exothermic reaction. In your vehicle, it fires the pistons. The fuel comes in, spark, right? That's the source of what? Your heat that we need, the spark, the rim that fell. So your plug sparks, the fuel is injected in, you have your, and this is all in your carburetor, you have your oxygen set just right, and boom, you get an explosion inside the energy, and that explosion feeds the energy back to the pistons. It starts to go, And people like me, a lot of piston action when we're riding down an open highway. Okay? All right? I was out in Montana, nothing but open road. That is not good for me. Okay? All right? I burn a lot of fuel. You get it? Pistons from this reaction. Exothermic. Yeah.
So could that be compared to like the water windmills in like Holland?
That's in fact what they're used for.
Okay, that's what I thought.
He just asked a question whether or not to be compared to the windmills in Holland. This is exactly what they're used for. Okay? They're used to turn the turbine, and in the second half of chapter 5, we're going to talk about that very concept of water turning turbines. But in fact, that's it, because the water has potential energy here, right? And as soon as it falls off the cliff, it has what type of energy? What are two energies? Kinetic. Now it has that kinetic energy, and when that kinetic energy hits the wheel, it spins it. And that spinning sends to a turbine, and it generates the sparks. The electricity start to move in the 3D structure around the building. We talked about the 3D structure. Electrons moving around, they move around, and you get the lights. But that's exactly what's happening. It's the same concept. That's exactly right. But instead of using a waterfall's kinetic energy, we use the kinetic energy of burning the fuel. You get it? But it's exactly the same concept. So yes, that is a concept. Here we show you how to do these conversions. We're going to spend time doing the conversions in another setting. Okay? It's what we do on homework day, and I think that's in a few weeks. Might be as early as next week. Can't recall. Okay? So we'll do these, but basically this converts it. This is just a conversion here. Okay? A few more slides. First part of this. So we have endo versus exo. So let's continue to talk about exo first, since we've kind of introduced that concept, which is the bottom part of the slide. In the exothermic reaction, from the system, it sends heat into the surroundings, or into the environment, or into the turbine. Okay? So the energy comes from the source into, and it goes out. It leaves the source. Follow? You burn your campfire, the energy comes out, it warms you. You burn your campfire, you put a marshmallow over it, you get your marshmallows, and you make your s'mores. You get it? So it sends the energy. So that's an exothermic reaction. Okay? For an endothermic reaction, it needs to absorb the heat to carry out its reaction. Okay? Photosynthesis is endothermic. Pretty sure of that. Okay? Photosynthesis absorbs the energy from the sun. Okay? Carbon source and oxygen, and created organic matter. Okay? You are organic matter, therefore we all matter. Okay? All right? So that's the difference between endothermic and exothermic. Endothermic comes into the system, exothermic goes out of the system. When we write a balanced equation, and next is going to be very important, get ready to make a note on this for those of you who are taking notes. I'm going to go back to this slide to illustrate it. We're going back to the slide entitled Hydrocarbon Combustion. So take a look at your slide entitled Hydrocarbon Combustion. I want to do this just to help you visualize what this looks like. If this is an exothermic reaction, and you want to note this, it is negative. Okay? It has negative energy. Exothermic has negative energy. Endothermic has positive energy. Very important to hang on to that concept, because you will be tested on it. You will have to use it. Exothermic has negative. Endothermic has positive. Okay. Right? Now, ready? Get ready to note the following. The next point. Here we go. When we write this in a chemical reaction, we write the energy. If it's negative energy, which is exothermic, we write it on the right side of the equation. So we would have you wouldn't put a negative sign though. You'd say plus energy here, plus so many kilocalories if it's exothermic. Does everyone follow? This is by convention. This is how it's written. It is negative energy because it is going from the left side of the equation to the right side. Does everyone follow? That's why it's negative. But when we write it with the equation, we write it as a plus energy on the right side of the equation. Everyone get that? By convention, you have to note the convention. And if you hear it enough, it'll make sense to you. That's because it is spitting the energy out. The energy is coming out as part of the product. Okay? Part of your product in an exothermic reaction is energy. So we say plus energy. If it is an endothermic reaction, which means it needs to absorb the energy to react, to do chemistry, photosynthesis, that energy is positive and the energy is written on the left side of the equation. So if it's an endothermic reaction, you'll see energy plus the rest of this. That's endothermic reaction, and you will see this on your exam. If it's an exothermic reaction, you'll see this reaction plus energy written here. It will not have a negative sign when it's in the equation. When we talk about it outside of the equation, writing the equation, we then give it a negative sign. So if it's written in a paragraph and you see negative energy, that's what kind of energy? Exothermic. Get it? If you read it in a paragraph and it has a plus, that is what type of energy? Endothermic. If it's written on the right side of the equation, that is exothermic. If it's written on the left side of the equation, it is endothermic.
Could you say one more time, the last part?
Yeah.
On the left and the right.
Yeah. If it's written on the right side of the equation, it is an exothermic reaction.
Okay.
If it's written on the left side of the equation, it is an endothermic reaction. Okay. And I think I warned you guys at the beginning of the semester that I do not have an indoor voice. And I apologize for you coming right off of spring break. Yeah, and you have to hear me. Okay, I know it's not easy. All right, I get it. All right. Here we go. So what happens and why does this energy do this? Energy changes at the molecular level. That's what we're happening. We're affecting the molecular level of this. And this is why chemists enjoy it, and that's why people like me smile when we talk about it. The energy changes are due to the arrangement of atoms of the reactants and the products. So you have these reactants. Reactants are always written on the left side of the equation. Note that as well. Write that down. Reactants are always written on the left side of the equation. Products are always written on the right side of the equation. Okay? So that's important to know. So we have this energy in this potential energy in these molecules, right? Because they just have the energy. They're the Krispy Kreme. They're just sitting there, not doing anything. You haven't consumed it yet. But as soon as you spark it and start to combust it, then you release that energy as kinetic energy, and in your machines, that's going to be exothermic. So bond breaking requires energy, whereas bond forming releases energy. Okay? All right? And that's worth noting. The breaking and forming of bonds dictates the direction, whether the direction will be endothermic or exothermic. If it takes more energy to break the bonds than to form new ones, it's endothermic. If it takes more energy to break the bonds than to form new ones, right, it's endothermic. You get it? If more energy is released to form new bonds, then it's exothermic. The key you want to look for those of you who look for these tags and paragraphs of how to memorize stuff, the word release is going to be a dead giveaway when it comes to exothermic reaction. It is rare that we can talk about exothermic reaction without saying release. And I do not try to write fancy, trick you questions. Okay, so it's almost impossible for you to miss an exothermic reaction because I have to use the word released, okay, or let go. Okay, but more time now I'll say if energy, I'll use the word released. You got it? It's hard to talk about exothermic reaction without saying release because that is what happens. And I don't try to think of these fancy sentences to throw you off on this. That is not my intent. Okay? So be aware of that. So we know if it's released, it's exothermic. If it's used and it requires a lot to be used, photosynthesis, then it's endothermic. And that happens at the molecular level where these are rearranged. These show you the bond energies. And why do we show you these? We show you these. We don't need you to memorize them. We'll tell you which ones by homework time, which ones we'll expect you to know. But we won't ask you to memorize these. So for the most part, the information on the left is FYI exposure. So things we want to expose you to. Bonding is the amount of energy that must be absorbed to break a chemical bond. You have to know that definition. Okay? Breaking bonds always requires energy. You have to know those two principles. That's what I expect you to know from this slide. But on the left, we show you that depending on the bond, there's more energy there. Does everyone see that? There's more energy depending on which bond. Here, these nitrogen bonds. Notice, you see these nitrogen bonds here? This nitrogen here? This is why it's used in bond making. Why fertilizers are used. A lot of energy stored there, right? Get it? A lot more than hydrogen. So this is why this is used, because there's a lot of potential energy there. And unfortunately, it's used for malicious purposes in many instances. And I think that's probably a good enough place to stop for today, guys. You hung in there. Thanks a lot. See you next time.